Yeah. 7 minutes already? Mm. Machine gun.
As it turns out, this is a trend that you really don't want to do. This is something that many people have been doing for a very long time, but it's become somewhat of a trend recently. This trend is called scalp popping. The way that you do it is you grab a small clump of hair, wrap your finger around it, and pull with a lot of force, like you're trying to pull the hair out, and it should make a popping sound on your scalp. A lot of people have been doing this because they claim that it eases your headaches or it eases your coughs, but there's no good scientific evidence to support these claims. And really, what it is that you're doing when you're scalp popping is pulling connective tissue off of your skull, literally pulling it off your skull. Specifically, the connective tissue that you're pulling from your skull is this one right here, the glia aponeurotica. It's a very fibrous tissue, and by pulling this off of your skull, you risk injuring it, potentially building up blood on the inside, or tearing your scalp. Here's a better clip for you guys to see the angle. Why What do you get when a bodybuilder, strongman, and a powerlifter enter a commercial gym? Gym members wondering what the heck is going on as they witness epic bench press max challenge. Stu just got done with the bodybuilding show, and John has never competed in strongman or powerlifting. It's always intriguing to know who would win a bench off between the different body types. Today, these members are about to find out as we start to motivate those around us. Stu is primarily a bodybuilder, so that was very impressive. Also, his max. I did a 225 pound for rest challenge a couple of days before, so let's see what he has. As the gym starts to fill up, Johnny and I start to power up. It's time for the main event. The lift was rough and it felt heavier than normal, but I'll take the max for today. It's Big Johnny's turn. The two members leave the gym with a new appreciation for strength and us three with the brothers in iron. The leader dose of caffeine for most people is around 10 grams. A cup of coffee has between 100 milligrams. That's 4 milligrams per cup. Only about 40% at least dose sugar. 5% of coffee. You know, I heard a quote one time from Vincent van Gogh that really rang true. He said, he has dedicated his life to his art. He has lost his mind in the process. When I sat and I thought about that, it sounded very familiar. I have given every single thing, every ounce of my life to this craft, to perfecting my craft. So, in the process, I have lost my mind to regular society, to people who wake up at 9 a.m., who clock out at 5 p.m. They would look at me and say, I've lost my mind. But me, I have found it almost.
Damn. I have found it almost. Jesus. But to me, I have found it almost.
You know, I heard a quote one time from Vincent van Gogh that really rang true. He said, he has dedicated his life to his art, and he has lost his mind in the process. When I sat and I thought about that, it sounded very familiar. I have given every single thing, every ounce of my life to this craft, to perfecting my craft, and I continue to do so. And in the process, I have lost my mind to regular society, people who wake up at 9 a.m., clock out at 5 p.m. I've lost my mind. With me, I have found it almost. The Irish mentality is when you finish school, you're not going to college, right? You have to get a job straight away. There's no chasing your dreams and doing what you want to do. You know, it's get a trade or get in and do a job. So I got the first trade. Not a good life to live, you know, and I just realized I didn't want to go down that route, you know. I thought I could do something with my life. The Irish mentality. Your arms are the only part of your physique. Sexism is alive in America. It's being oil states and all whites this scale laughed at me and told me to get probably jealous I drive a Tesla and they not the woman.
Tesla.
Hello, Christopher. Hi, how are you?
Not bad.
Okay, good. That sounds good. Okay, I just saw that you sent it to me. I will look at it, then I can give you a feedback if there's any for next time, huh?
Yeah.
From what you just sent me. All right, so then we can go further into the density, pressure, and so on. We can work on a paper. Today we have anyway 1 hour 45 minutes, a bit more than usual,
Oh,
because the next lesson is Sunday in a week, right? You have no lesson the next Friday, because I think you're some school event, I think, and and we have it on Sunday day in a week, but it will be a bit less for me, so I'll do the 15-minute more today, huh? So to make it 1.5 hours in the end, nevertheless. Okay, so you see, we do the multiple choice actually. It's called medium. There depends a bit. Some of them are a bit more intensive, some a bit less. The point is, of course, with all these multiple choice, they're not necessarily easier than the not multiple choice questions. Just that you have 4 answers to choose, but in order to get the right answer, you have to usually make quite some calculations. So usually that 1 mark is a bit misleading because yes, all of them give 1 mark in tendency, right? But the level of what you have to do is not reflecting the 1 mark, or the other way around. 1 mark is not reflecting how much you have to do. That would be a bit different in a so-called non-multiple choice test paper. But the marks don't really matter in our content right now. It's more about, well, doing some exercises, huh? And okay, let's start with the first one. I just let you read it. So, have you read it, Chris?
yeah.
Okay. So, what do we have to answer? What do we have for A, B, C, D? What is the core of the question?
I think we compare the density when they're comparing the upthrust of water on the different rods.
Okay. So now you said basically two things. So which one is the key matter which we ultimately have to look at in order to give the answer?
The density.
Just look at A, B, C, D once more.
Upthrust.
Upthrust, exactly. This is exactly one of those. That's why the multiple choice questions are usually a bit tricky and sometimes challenging too, depends a bit. And you can see the moment you see, okay, I have to answer about upthrust, not necessarily the value. That's the challenge for the multiple choice questions usually, but comparing something to something, but all related to the upthrust. So the bottom line is, of course, in order to do that, I have to figure out how do I calculate the upthrust, and less in values. That's only the second step, but more or part of values actually. The first step is really to get a relationship of how that upthrust is being calculated, and then I can put that into perspective, and then I can calculate it. Huh? So, what is the most simple way to calculate the upthrust? Or when we look at density, so we probably have some, and depth, we probably have some, and areas are given as well. So what is probably the relationship to calculate the upthrust or the force?
Um,
In its most simple form, huh? Then we go a bit more to the next step.
So it's the pressure of the water minus. Wait.
Yeah, okay. I would go. It's a good start. Pressure. Okay. So, what is the most simple definition of pressure?
Force applied per unit area.
Okay. So force over area. All right. So that helps us already quite something. And that's one way. And there's a second equation, very typical, right? How else can we calculate the pressure when we think about density and other factors? Like in that very specific situation of upthrust, but we think still of pressure first. And we have submerged objects. So how does that pressure work like for that situation of submerged objects kept at a steady level?
The heights are all the same.
Okay, yep, heights are all the same. So height is something we have to consider. What else?
The density of water and the
Okay,
gravitational pull.
exactly. Yeah. All right. Okay. So we see we have that's a very standard approach somehow, having two different equations for the same, but we look at it from different angles, right? Here we are focusing on the force over area. Okay, that's pressure, and on the other hand, in that specific situation, how deeply is it submerged? Of course, gravitational force has to come into play, or force field, and of course the density of the water. And then we have some information where we put that into relation to what happens with the various objects. So now if we combine, I'll make it a bit, let me write it right down once more. So pressure, I already wanted to change it. Pressure, force over area, and pressure is density times G times H. Okay, so how would we now, and we have concluded what we are interested in is the force to answer it. So how do we rearrange our equation so that we get all the information we have at our disposition and can answer the question ultimately?
So the density times acceleration times height times the area.
Okay, all right. So I just go one step further and just go with the first one. So I just take this one and then, like you just said, answer we can then replace this one times a. So step by step. All right. Okay. So we have a nice equation which tells us, okay, how's the upthrust, the force related? Now, of course, that's part of the question. What is, as we compare these four objects, what is obviously now the one which gives us the force? Or the different force from one object to the other, or in other words, what is the same for all the objects?
Their heights and the area is the same.
Okay, right. So we have the height is the same. Sorry, that should be right. So height is the same, area is the same, and anything else?
The gravity also the same.
Yeah, exactly. So in other words, we can say in that regards, it's proportional to the density, right?
Yeah.
And so directly. So we can actually even say, well, directly, right? Of course, there's some constants. So, or the way we can write it as well is something like force is equal to the density times some constants, which are obviously these. You can refer to them as constants. So they don't matter in order to differentiate between the A, B, C, D, or the X, Y, Z, W objects. So as we now say, force is proportional to density. So, and now we have to, of course, and now comes the complicated stuff, kind of, for the multiple choice. if we would have a non-multiple choice, then it could be, for example, which one is has the strongest force, or the opposite, of course, the smallest force. But in a multiple choice, they usually make it a bit nasty and compare stuff with stuff, right? One object to the other, etc. And so we have to go basically through all four. That's why the 1 mark is really misleading. We have to make quite a couple of. So we have to identify this, have to identify that, put it into relationship, rearrange it, come up with this one, and now go through the answers. So that's at least 4 marks. So which one? And now it becomes a bit tricky as well. Which one would you now say is the right answer? And then we go from there.
C.
So Z would be double the one on Y. It's it's really a tricky question, huh? What is the key to the answer, Chris? So what is
I don't know, because upthrust, does upthrust just mean the force generated by the pressure of the water, or is it the
Yeah, this is a good question, right? That's probably the very okay, let's go step by step. On one side, we see they're all held in the same depth, huh?
yeah.
So that, which means an external force must hold them in place. Otherwise, they would not be held in place, right?
Yeah.
So on the other hand, the pressure will be the same at the same depth. That is the tricky part, right? And that answers your question, actually, right?
Oh.
Exactly. So this is right. Yes, there is something we have to say, but the density is the one, like you said, it's the one of the water, right?
Oh yeah. So they're all the same.
They're all the same, exactly. Huh? So this is really a nasty one, kind of, right? So we have to really work our way through. I mean, of course, and the reason why we went through all the calculations is just, well, that's what we usually do, right? We think about it. Okay, let's take the formula, let's put it into relationship to each other, rearrange it, and come up with that one. But like you said at the very beginning, the density, right, is, or in between, said it in between, of the water. And well, let me see, we had it somewhere at the beginning, I think. No, that was pressure. Sorry. So it's the density of the liquid here. Pressure, Archimedes, exactly. So the tricky part is always the density of the water. So that's why the reason why, and a simple mind hook is actually to think about, well, if you think about a swimming pool and about the sea, which and let's say it's a calm sea, etc., not with choppy waves, then everything's of course a bit different. But a very quiet pool, a very calm, quiet sea. Which one usually gives you a bit the better upthrust, the pool or the sea water? I mean, the pool water or the sea water?
Probably the seawater because it's denser.
Yeah, exactly. Because and why is it denser? Why does it have the higher density?
Because it contains like the salts and stuff.
Yeah, exactly. Huh? Exactly. So that means, have you heard about the so-called Dead Sea somewhere in the Middle East?
No.
Okay, yeah, that's one. Well, it's actually more kind of a lake, but it's still called a sea. I think there's a certain channel connecting, but whatever. And that one has a very, very high salt percentage content. So basically, there you can truly float without moving anything. But even in the sea, we have to move, otherwise we submerge. We have to create some upthrust, so to speak. But in the Dead Sea, you can actually float on your back because the water, the salt water, has such a high density that it generates an upthrust in order to float. And of course, that's not true for everybody in the end, because we know the volume has some impact of the object, right? Of how much volume is being pushed aside, right? That is the key. So that's like good old Archimedes to keep in mind, to say, well, this is the counter. That's why this one is so decisive and gives us the way to go. And of course, typical multiple choice questions are usually a bit misleading to some degree. It would make no sense, on the other hand, to ask that question as a non-multiple choice question, kind of, right? In that regards, we probably would come to the answer quite fast, but of course, with all the statements here and all these statements here, leads us into a comparatively wrong direction. Huh? Okay, yeah, that's good. And so the point is, so nevertheless, of course, this is still true, right? Directly proportional to the density. And that's exactly what we just discussed in terms of the sea and the pool, right? That is because the density of the water. So this is still true, but yep, the density is something which doesn't depend on the object. It really depends on the liquid.
Yeah.
The volume, however, is a different story then, right? That is for sure. Okay, let's go into question 2. That's actually quite an interesting question. Some may solve it with, how to say, intuitive thinking at some point, but we would like to do it by calculation. So what is the formula basically, or the relationship we have to consider in order to come up with the answer? This time, no tricky thing.
So 100,000 Pascal plus
Okay.
the density times height times g.
Yeah, exactly. Okay.
Equals to 150,000.
Yeah. Very good. Okay. Okay, that means, so our depth, no, we want the depth, sorry, not the density. So how do we calculate now the height or the depth in that regard?
50,000 divided by 9.81 times 1,020.
Okay, yep, 1020. Yeah, important to make sure which it is. They have kilogram per cubic meter, so that's fine. And what depth do we get roughly? Or precisely and then approximately?
Wait.
Do you have it, Chris?
I'm using my phone calculator, so it's hard to.
Okay, yeah. Do you have a scientific one when you tilt it? You know, some of them, when you tilt them to the landscape mode, then they become a scientific calculator. That makes life easier, usually a bit easier for such calculations.
I think it's 4.997.
Okay, meters, huh? Okay, all right, so we can say approximately 5 meters, huh?
Yeah.
And that's now an interesting relationship, actually, we can conclude, just as a rule of thumb, frankly speaking. When you look at what is the pressure difference again?
50,000.
Between 50,000, okay, yep, 50,000. So let me go back and write that. So the delta P, so our pressure difference is 50,000, huh? 50,000. Or let's say 5 kilopascal, 50 kilopascal. In that context, it's maybe as well. Well, okay, now let's leave the 50,000, doesn't matter. Okay, Pascal. And the delta H is 5 meter, huh? So what relationship can you say as a rule of thumb?
Every meter is 10,000 Pascal.
Exactly. Yeah, very good. Exactly. And now I'm just write it like kilopascal. Huh? Exactly. Huh? So so every meter we dive is 10 kilopascal. That means if we dive 10 meters, then what do we have? Which pressure do we have compared to the surface?
100,000.
Yeah. And what is that equal to? Also, if we add it, so if you
200,000.
think about the, yeah, exactly right. So we have 100 kilopascals. We go down 10 meters, and we end up on 200 kilopascals. So in other words, we double, or add 1 atmospheric pressure per 100. That's then another way to phrase it. So if you're a diver, actually, when you dive down after 10 meters, which is not that deep, you already have double the atmospheric pressure from the surface. If you dive down 20 meters, it's already triple, etc., etc. So if you dive down 50 meters, which is already quite some depth, actually, which you can only do, of course, with this oxygen tanks, that means you're under plus 50,000, right? 60,000, so 6 times the atmospheric pressure, which means your system will take up much more oxygen. That's the point. So if you take in more oxygen because of that pressure, that means you have to be careful when you go up again. So you cannot just instantly whoosh, compress, so to speak. That's what it's called. So as a diver, you cannot just go, say, from 50 meters below instantly to the surface. You have to time it. I can't remember what the decompression time is per 10 meters, obviously, but there's a rule. That's why the divers have these special diving watches, actually, which then tells them, okay, A, I need, of course, to know the depth I am. B, under what is the time I have to wait on every 10 meters, let's say, keep it simple. Maybe a minute, maybe 2 minutes. So that means has an impact to calculate your oxygen reserve, not that you dive down all the way within, say, diving down is not so difficult. The pressure difference is okay. So you can dive down in a couple of minutes, easy, 3 minutes, make it 5 minutes. Then you dive around, explore something, and then you want to go up. But then you have to make sure that the reserve, of course, of oxygen is as such that you, let's say, can decompress for the next 20 minutes. I mean, again, my relationships are made up right now because I can't remember it, huh? So that you have enough oxygen in your tank so that you can do the proper decompression. Otherwise, you may get some health damage, actually. Huh? So that is quite a practical question, actually, even if they don't really voice it out here. Huh? Okay?
Yeah.
All right. Now, that's another one. So you see now we go from deep diving into particles, alpha particles, and which actually is a proton. They don't say it here, but it's a proton. And it has a pretty high speed, obviously close to the speed of light. And now they collide. So this is an interesting question in regards to when we learn about the various types of a radiation or particles and what stops them, right? So this is now basically a practical calculation of how to well, either dimension it or what type of pressure it has to withhold. So here we focus more on the pressure. So I mean, this is clearly not just a one-mark question in terms of difficulty. But we know we talk about pressure. So what is a good approach to for the pressure starting point?
So just use force over area.
Yeah, it's always a good approach. It's always a good start. Always start with the simple part and say, okay, so now on the other hand, the force, how can I think of the force? What is another way? So, of course, you can rearrange the force, but in this case, no need, not like in the first question. In this context, how can I define force as well? When you think back to Newton, there are basically two ways to define force.
Momentum transferred per second.
Okay, very good. So we can make the delta P over the delta T, exactly. So now we coming closer. And when we now the third one, this is the overall force, right? So okay, momentum. All right. So we talk about individual particles now. So, and they say a beam of particles, and they even give us a number actually, pretty big. Well, not that well. 500,000, sorry, 50,000 particles. That's probably not so much. So obviously, the pressure is a result as well, or the force is a result as well of how many particles are involved. So having made that connection, we have to think, then what is then the force due to one particle? Or in other words, how can I extend my delta P, so to speak?
So each.
Or it is the same in the end.
Each particle.
Okay. Or I could just make it as one alpha. Huh? One alpha. Okay. Yep.
Each particle is 6.6 times 10 to the power negative 27 times 1.5 times 10 to the power of 7.
Okay, all right. Or
momentum.
okay, what you told me this. Okay, exactly. So m times v, huh? Important. Yeah, that's very important. And over time, of course. Huh? So here we disregard the delta t. We just look at this. Yeah, it's of course the same. Okay, so now we're coming closer. Now, in order to go from per alpha, so to speak, into the total, what do we have to do with the force per particle?
I think we have to do times the amount of particles first, because it says the amount
Yeah,
of particles
very good.
per second.
Exactly. Yeah, exactly. Huh? So this is then amount per particles per second. So this is thing to keep in mind, that we are not just thinking particles like a quantity. So that's just no dimension. It's just, well, 50,000 particles, for example, or 500,000 particles, whatever. But it's clearly said per second. So that's sometimes a bit, it's very good that you mentioned that. So to keep in mind that per second. Huh? Because sometimes that gets lost, and then suddenly the units of measurement don't make sense anymore. Because we only have a counter, right? 50,000 particles, okay, all right, but per second. So obviously that will then have an impact when I look at my different times, etc. Okay, so we have times that n, huh? So I call that n, which is very common actually, that we call the number of particles. But sometimes it's just a number of particles. That's more the case in chemistry in tendency, but here we have to make sure that it's per second. Huh? So it's like a flow rate to some degree, or a mass flow rate times n. Huh? Okay, so now do we have everything we want? Probably yes. Huh? So then let's start. I just put it into a final formula. So we started with f over a, which led us to the time that we said, okay, we have n. So n is this one, so, and n per t. So that's the one we have to be careful with. So in order to make it extremely precise, I already introduced the numbers per time as like what I just wrote down. So not to forget the per time eventually. And then we have, of course, our n times v. Anything else? Maybe do it like this. So maybe better put it into brackets here. So this is per time. Per time. And when I look, so I had n, f, I replaced my force with delta p, mv times t. So I put that here. And of course, I still have my my area. Huh? Okay, that was wrong color. M times v over a. So in tendency, we, of course, as we have all the values given, there's no need to substitute. And hence we can just introduce the items. So we have this like 5 times 10 to the power of 4. I just put it in brackets to separate one from the other. Over times mass. So you mentioned that before. So 6.6 times 10 to the power of minus 27 times 1.5 times 10 to the power of 7. And anything we have to, or I make it just like minus 4, huh? Because everything's in powers of 10. So I just take it into power of 4, right? It makes it a bit easier. Just to keep in mind the 1 centimeter first, and then it's cubed. No, not cubed, square, excuse me. Okay, so now I will just jump ahead to the final number. So that will be 4.95 times 10 to the power of minus 11, because everything was in the right time unit of measurement. So we can come up with Pascal, or kilopascal, or whatever. So which one is therefore the correct answer?
5 times 10 to the power negative 11.
Okay, that would be answer
C.
C, huh? Okay, yep. Exactly, huh? All right. Pascal. So far, so clear, Chris?
Yeah.
Okay, yeah. I mean, the key point is to have, clearly we go already one step further, but you see as well in pressure, there's quite often the momentum involved, because we talk quite often about collision, like here, about particles. Could have been two balls made of steel or whatever, a billiard player, whatever, something like that. So the momentum is, you see already, it's an extension of the pure density question to link it up with something we already know from before. Huh? Okay. Question 4. So this is, I mean, the questions are quite interesting from a practical point of view. Somebody, well, makes a borehole, and as usual, it contains not just oil, it has water as well. So we have to see a bit, pressure-wise, what happens here. So you see the pressure is quite large, right? Megapascal, not just kilo Pascal. So that's quite some intense pressure down there. Then we have the density and the density of water. And you can see an interesting relationship as well. That water is actually denser than oil. But just before we go into that question, Chris, when you see that density of the oil is less than the density of water, what, in case of we see that unfortunately once in a while with a ship, maybe there's oil leaking, or even an oil tanker is crashing, whatever. What does that mean when the oil is leaking from the tanker? What would you expect? Say again, sorry?
It will float.
It will float, exactly. That is good and bad, unfortunately, for some sea creatures, birds and so on. But on the other hand, it makes it a bit easier to collect it, huh? That's why they can, if the sea is quiet, of course, that's a different story. If there's a choppy sea, then it, of course, gets mixed up. And then other stuff may happen. But in that case, they can kind of contain it with some kind of barriers, huge barriers like plastic ones, contain it, and then typically nowadays they will release some bacteria which are happily feeding on the oil, and in order to contain it. Huh? So that's some side effect of some simple, basic physical situations. Otherwise, if it would be heavier, it would be a very different story. Okay, now to the question.
So it's the density of oil times x times 9.81 plus the density of water times bracket 2000 minus x times 9.81.
Okay.
And equals to the 17,500,000 Pascal.
Okay. All right. Very good. Okay. I will write that down in a step-by-step approach. Just make sure, Chris, that when you in test, always write it down. You're very fast, which is excellent. Just write it down step by step. It always helps in case of correction and ultimately with some number problems eventually, right? So we started with the pressure, that's good. Then we can obviously say, well, I have the density of water, I have the depth of the water. And what is the depth of the water, Chris?
It's 2000 minus x.
Okay, minus x, all right. Of course, that's then the, what do we call that? Water, let's call it W, of course. And the height of the oil, that should be an O. What is the height of the, I mean, it's very obvious, but just nevertheless to state it.
X.
X, huh? Okay, so in other words, actually, so there's a nice link between these two, and the unknown is an X. Well, there's a reason, obviously, why they call it X. So we always have to solve one equation for X. Huh? That's actually standard procedure. Okay. And of course, the pressure is a general one. So we just obviously have different heights and different densities because we have different liquids. Huh? So this is now one question where we deal with different liquids, which is the only way to deal with different densities. Huh? Okay, and now clearly we have to put everything together. So you said it already on one side, so we already have the 17.5. I just put it down in powers of 10. That is equal to what? If you can just briefly say, what is that pressure, which is at the bottom? So we have basically that pressure. Well, basically we can call that at the bottom. It's this one. And what is it made of? Which two pressures will contribute?
Pressure of oil and pressure of water.
Oh, exactly. Huh? All right, exactly. And here we just have the general formula, so we can as well call it PI, for example, which is depending on these two, right? We have the density is different because we deal with two different liquids, and of course the height is different, whereas the G is a constant. Huh? So we could as well take out the G eventually to make our life easier. That's in a matter of math, if we want to do that or not. Mathematicians, of course, they like to take the G out of it. Then when we add them up, in physics, we may separately calculate the pressure because we would still like to see eventually the different pressure which is being generated by the oil and by the water. Of course, partially due to the density, and of course, partially due to the different depths we are talking about. Huh? So that's why in physics we rather don't take the G out because we still are interested in the individual values. Okay. So now you basically said it already before. So the oil is of course 830 times 9.81. Anything I forgot? Times x, of course. Huh? So make that a bit. That's the dot times x. Huh? So plus. Then we have, of course, 1000 times 9.81. And we have, of course, 2000 minus x. Okay.
Oh, wait, near the zero, like 2000.
Thank you. Yep. Okay. All right. So math problem, huh? Where we probably so now because we don't have our x, so it would be nice to calculate the pressure separately. Unfortunately, the x is the one we are looking for and not the pressure. So hence, we probably rather go math. Take the 9.81 out, the g, so to speak, and then rearrange. So what would be the rearrangement in the end of our formula?
So then they all the 9.81 is gone from the right, and on the left is divided by 9.81.
Okay, so we can already go for that one. So I will already start something like this. Huh? So which is 9.81. Okay, good one. But maybe okay, how would you, or how do you deal with the let's say with the X problem? What do you suggest, Chris? How should we deal with that? I mean, to isolate X, I mean. When you look at what we are having on the right side, or in the second term of the right side.
I would times 1,000 with the bracket, the 1,000
Okay.
times 2,000 minus
Okay.
1,000
Yep.
x.
Okay. Exactly. So there's no way around it actually. Exactly. So we have to calculate the two parts. So then we have, of course, just 1,000 times 2,000. That's just a constant value kind of. And on the other hand, we have a 1,000x. And obviously then we have a nice solution taking that one out, as we said before. So we have 830 times x minus, obviously, 1000x. Do you see that as well?
Yeah.
So because we took over the 9.81, so we have 830x. We have plus 2000. So we have, what is that? 2 times how many? Power of 10, how many? If you calculate 1,000 times 2,000. These two.
2 times 10 to the power of 6.
Yep, exactly. And then we have then the last one, right, is obviously 1,000 x. All right. So actually, not that wild, so to speak.
You also missed a 0 on the 1,000.
Yep. Seems to be my non-zero day. Okay. All right. So, and of course, we can see already at 30 minus 1,000. But probably because we rearrange it for the x. Sorry. We yep. So one step too many. So actually, it goes the other way around in that regards. And okay, that was a jump too fast, actually. So, oops, let's like that. So we have already taken out 9.81, so it's already 1. The 17.5 over 9.81 times 10 to the power of 6. And we had what we calculated here, 830x minus 1000x plus 2 times 10 to the power of 6. All right. That one gives us, of course, 170x minus plus 2 times 10 to the power of 6. Okay, so what else to be done, Chris?
We move the 2 times 10 to the power of 6 on the other side, so it's minus 2 times 10 to the power of 6.
Okay. Okay. And then?
and then we divide the whole thing on the left by negative 170.
Okay, yep. Okay, times 1. Okay. Here we just say minus 170, yeah? Okay. All right. And what do we get in consequence? So if we now make it, so, oops, because we now we have that. When you look at it, we need to have a depth, right? And because we said the plus direction is clearly going down. That's our plus. So what can we do with the minuses now, Chris?
We cancel out. Or no,
Exactly.
no.
Just take. Yeah, we can take it away, right? Did I hear you right?
Well, I think when you calculate it, it's going to be positive.
Exactly. Yeah, because you can see it's a minus on the upper part and minus on the lower part, so that will result in a plus. Or you can as well look at it and say it actually eliminates itself, right? So it's two ways to look at it. Minus divided by, yeah,
that one's plus, like minus 2 times 10 to the power 6 plus the other one.
Yeah, exactly. My bad, genau. So you're right. So plus this one. But no, sorry, oops. That was my bad. Actually, yep. So we had that minus first, but then divide by 9.81. Still, so okay. Yeah, I didn't write it really properly because we jumped one step. Not really, we jumped, but the way to write it properly, I have to write it here on top. So 2 times 10 to the power of 6 plus, and this is minus, huh? Because it was taken over to the other side. We have to be careful with the 9.81, right? Because it had 9.81 as well, right? The 2000 here. So hence, as we divide it, it will be on top of the division as well. You know what I mean?
Yeah.
So that's why the yes, you're right with the plus here, and of course this one will result. We have minus 2 plus 17.5, and that's the beauty now you can see of the powers, right? Because they are both 10 to the power of 6. So actually, I can eliminate them. And just calculate 17.5 minus 2. Okay, so when we've done all that, then that's why we can eliminate the plus, the minuses, and we should get actually 1,271 meters. Okay, do you get that as well?
Yeah.
Okay, all right. Okay, so Hainsworth, obviously, clearly it's question answer D. So, all right, good. Yeah, I think it plays well with the various elements of when we see pressure and density, and puts that into some calculations accordingly. So it becomes then more of an issue to make sure we do the calculations all proper. Huh? Okay. Would you like to have a brief break, Chris, or just continue?
Because yeah, I want to go wash my eye.
Yeah. Okay. Yeah. Just give you the break for 1-2 minutes, huh?
Yeah.
All right. Mm.
Okay, I'm back.
Okay, great. No problem. Good. Okay, so now we probably, let me see, there are typically 9 questions. Okay, yep. Let's do this. We do more questions. Today is really all about questions, answering about that. But we probably after this 5th one, I think we probably go into the hard one and see how we can go there, huh? So, because this is a so-called medium level, which is it's medium plus probably. But for you, it goes very well. So let's try then the next level. But let's go this one. This is a very typical one with the various air pressures in the pipes, stuff like that. So we have 2 bulbs. They have obviously different air pressure. I mean, obviously half of the other makes it a bit easier for the calculation and the relationships. And we have mercury. Okay, so it's like, for example, an old style fever measurement device. Of course, it's not, but just to say why the mercury is like that, they probably have to indicate something. For example, the air pressure. So that might be something as a device to give us an indicator of the air pressure in the surrounding related to a reference air pressure, for example. Could be. And you see the density is quite something, 13,000 kilograms. So, yeah, no wonder. It's quite heavy. Liquid lead, kind of. And we want to know H1, H2. What is the proper pair in relation to the situation of the pressure situation? Obviously, double pressure between the X and the Y. And how should we start to deal with that, Chris?
Uh, uh, because like the um like the bottom part of the two like tubes, they're not on the same level.
Okay. Yep, that's influenced by the pressure. Yep, that's a good one. Right. But I mean, I don't know how you see it, but if you see the higher pressure here, I mean, in terms of how you perceive it, how you think about it, when you have the higher pressure, but it's not to scale. So it's sometimes a bit difficult to say, right? From this scale, it's not to scale, but at least from a potential point of view, it seems that this one is a bit higher up than that one. Huh?
Yeah.
So that is probably, well, it's a question, but in the end, we are interested in the difference between the two. So it's a relative question. It's irrespective of how high up this one is and how low this or whatever, the other way around. What counts is that basically, let's say the delta H, the difference between the two tops. One is exposed to this pressure and that one, and the other one is exposed to this pressure and that one. And of course, the height clearly results in force, in pressure, which has then to be, well, kind of counterbalanced with the pressures we have from the bulbs. So when you look at the, let's say the pressure here, right?
Mm.
Or the pressure there, because that's where we can at least link it to what we typically know. What must be the pressure there? What kind of formula could you create in order to express the pressure at that point?
Well, at that point, I think it's just the values provided.
Okay, yeah. So when you say values provided, what would that you mean? Like the typical pressure equals, I mean, just write it down, right? Like this, right? That would be the starting point.
Because at the bottom parts, I think that it's just directly being pushed by the 16,000 Pascal and the 8,000 Pascal pressure.
Ah, okay, yeah, genau. It's not. That's exactly the tricky part here, right? I mean, you see how the various questions deal with different aspects, right? Here we had to introduce, yes, of course, pressure equals density times G times H, but we can, and of course we can say this is true for both parts. So we introduce the I to say this is water or oil, which obviously leads to a different pressure. Okay, so now here we can, of course, the key part is we have the same material. Okay, there's no different. This one, G, is the same. So obviously the height is the only variable. Seems to be, huh? That would be too simple, kind of, when you have such a construct, huh? Because we cannot. Do you have? Let me ask the other way around. Is there any pressure here?
Yes.
Exactly, huh? So, and in point P, we can assume there is an even pressure inside that section, outside the mercury. So, will that henceforth have an impact on the pressure here?
Oh. No.
If there would be no pressure here, what would happen?
It'll flow into there.
Yeah, genau, right? So the point is that if you would have only this pressure and only that pressure, whereas obviously this one is double this one, so in tendency it would start to push it over, right?
Yeah.
So that the mercury here, because there's no resistance, so to speak, in between, so it just flows, but it's not. At least that's what we are being told, because for some reason there's a pressure kept in here. Maybe just the original air which was in there could not escape. Right? We don't know how the mercury came into here actually, but somehow we could expect that maybe it was poured in here, pushed up, whatever. But obviously, there's no vacuum. I mean, if there would be a vacuum, there would be basically no pressure. So it's obviously not, because it's explicitly said that there's containing air at different pressures, the two bulbs. So it's not quite complete, because we would have to say, well, actually part P contains something as well. So the information given is a bit incomplete, because it says explicitly we have air with a certain pressure here, we have air with a certain pressure here, because it's all connected, so pressure is everywhere the same. And on the other hand, of course, we have some pressure here as well. Huh? And that is the one part where we have to be a bit careful with, to say, this tube P actually must have some pressure as well. Now, when you think of the pressure, you have pressure here and you have pressure there. So in order to express the pressure at that point, it's clearly our 16,000.
Yeah.
But it's reduced, so to speak, by the pressure exercised in P from P. Or in other words, I can say at P, there's a pressure of small cap P. I mean, not very innovative, but makes life a bit easier. So I can say there's the pressure here is minus P, and the same thing, of course, happens for this one. It's 8,000 minus that P.
Yeah. So, so then they equal the height times the density, and then
Exactly. Very good. All right, and then we have our 1 times G times H1. No, that looks like a 1. So let's make nothing, just G H1, and here it's the same, G H2, huh? Okay. And if we now of course, we have two equations. No surprise here, so to speak. That's what we need. And now we can rearrange. So we want to know the pair of which value. So we want to know explicitly H1 and H2. Huh? And Ainsworth, just purely mathematically speaking, we need two equations. Otherwise, we can't figure out H1 and H2, right? So two unknowns means two equations, which we have generated. So that's the key step, actually, on one side, and we have to link them. And the key was to realize the pressure from here contributes actually to this one. That is not so obvious at first glance. So it needs some exercise to discuss that, as it's not necessarily covered in the theory, first of all. So how should we rearrange the whole equation now?
So when 16,000 minus the first pressure, the
Oh, how would you rearrange it, Chris? What is the one which is bothering us? Because do we know a small cap P?
No.
Exactly. Yes. And do we need to know it?
No, we just have to know. It just connects the two.
Exactly. Yeah, very good. Exactly. That's the connecting point. Exactly. Huh? That's where we can link the two equations with each other. Huh? So this is all the exercises we did in the past in math, when we had to substitute one equation, rearrange one equation and put it into the second equation in order then to get the x1, for example. And then out of that later on got the x2. It's nothing else but a practical application here, huh? Which is the link to math as well, so to speak. Okay, yeah, so we can rearrange it. How would you rearrange it? It doesn't matter which one, right? We can just start with one, it doesn't matter.
P equals 16,000 minus the rho times P times H1.
Okay. So, or would you say, because it's minus P, you know? Yeah, right. I mean, if you look at it, here we say 16,000. So typically, I would like. Well, of course, you need. It's a minus P you need here. So actually, what you can say is, I leave my minus P and I minus my 16,000. But I mean, either way, right? It doesn't really matter. Just to give you an idea, right? Sometimes when we see something minus here, we can actually utilize that and leave it like this. Otherwise, I would rather recommend make this into the plus, right? And then move the rest accordingly. But okay, so let's say we have minus P, then I would go the other way around. Huh? Let's say we have our times H minus 16,000. Huh? Okay, and Hainsworth, we would have 8,000 minus H1 minus 16,000 is equal to H2, huh?
Yeah.
So far, okay? I think so.
Yeah.
Okay,
wait,
then
should it
we
be plus? Because it's already minus there.
Say again, Chris, sorry?
Because it's already minus P equals that, then when we substitute it, should it be just directly plus the bracket? Because it's 8,000 minus P.
Very good. Yep, exactly. Yeah, exactly. So I made the double mistake. Exactly. Yeah, very good. Exactly. So if we go minus P, then go minus P. Yeah. Plus minus. So that's yep. Okay. So therefore we have 8,000 minus 16,000, and that equals what now?
H2 minus H1.
Okay. Yep. H2 minus H1, and times what? So I have hardly any spare. I was a bit too generous. Okay, minus H1 times our not to forget the constants, huh?
Yeah.
Because we need them again. Okay, so obviously we have now H2 minus H1, and seemingly H2 is shorter than H1, so we can as well revert it. Doesn't matter actually. Either way, we can either now make it 16,000 minus 8,000, but then H1 minus H2, but because it seems that H1 is shorter, but we don't know, so we can of course leave it in doubt. Either way, it doesn't matter. So we have minus 8,000 divided by this one is equal to our H2 minus H1, huh?
Yeah.
Okay, and what do we get for that? For that delta H?
Oh. Wait, I got negative 0.05996.
Yeah, okay, yep, that's okay. 0.059, huh?
0.6?
6 even. Yeah. So that's We can as well say minus 0.6. The minus only comes from the direction. Excuse me. Comes only from the direction, right? So that is something which minus 0.06, which is 6 centimeters, approximately 6 centimeters. But because we said H2 minus H1, right? So you see, when you now look into the table, it's just a matter of which one do you deduct from what, right? And you see that as well, difficult to say. Can't really say it like that. We have to be careful that we say minus 6. Because delta H is really H2 minus H1. So, of course, we could now go backwards, but what do we do as a next step, Chris? What would you suggest? How do we deal with that information?
H1 is bigger.
Okay, minus 6 centimeter, okay. So H1 is bigger, so okay, so H1 bigger than H2. That's one thing.
I think H1 equals to H2 plus 6.
Exactly. So we can say, well, if H1 is bigger than H2, so this is a potential one, and this is a potential one. Huh? This one, no, not really, because we have a difference. So this one is out already because we know it must be a difference. The heights, there's a height difference in short. Okay, so we have to nail it down to 2, A or D. Now, which one is it?
D.
D, yeah, exactly. All right, good. Because if we do the H2 minus H1, we get the negative value in the dimension of we want it, because this one is only delta 2, obviously, and this is delta 6. Huh? Exactly. So it's a bit, in the end, it's a bit common sense logic, kind of, in order to come up with the solution. Not, well, of course, in the end, it's math, but from the application. So the trick was to realize, all right, there's another pressure involved, which needs a bit of consideration and thinking to say, hey, wait a minute, if I have no pressure here, that stuff would not be holding place here. That would guarantee, then it would just be, well, one pipe, so to speak, right, all the way. And then, of course, the height would be a bit different, which quite often is the case as well. If it's filled here, then we have that, like, say, with that principle, it plays as well of equalizing, for example, the level in certain devices, to make the same because of the pressure. But we don't have mercury here, so that's a very important information which is not really explicitly said, so we have to realize that. And then the next step is to say, okay, henceforth, the pressure is therefore a matter of including that small pressure I keep here. Huh? The rest is standard. Then, of course, and then the one which is not quite standard is to deal with the height difference. Of course, we could calculate them individually, like x1, x2, h1, h2. We have two equations, no problem. But we don't have to go that far, because we can as well go a bit of logic, leave it with the difference, and look at the delta. Okay. Let me see. No, let's do number 6 as well, because the interesting here is now we have a mix. That is something different. You see, every question deals a bit with some different basic principle. Now, what we have not encountered yet was the mixture of two liquids with different densities. And we want to calculate the density of the mixture with a given volume, of course. So that means, obviously, we'll see as we go ahead. And what would be the starting point for that calculation, Chris? It's always the same question, not the same answer. The same question. What do we have to look at when we look at that density of the mixture?
I think we find the mass, total mass.
Okay. All right. Yeah. Good. Sorry. Yep. Total or mix. Let's call it M for the mix. Huh? Is the mass of the super of the mix. Then make a capital over what?
Over the volume of the mixture.
Over the volume of the mixture, or we could say as well T for total. It doesn't really matter, but important that we give it an indice in order to make sure, we really talk about the mix or the total, not that we suddenly only think about alcohol or water or whatever. All right, okay. So, how do we now come to the? Obviously, we need the masses, right? So we obviously need to have the mass of the alcohol. We need to have the mass of the water, and well, the total volume is a given. So that's easy. So we can as well say this one is the green one because this is a given, whereas this one is red. Huh? So we need to know that. Do we know the mass of the alcohol or the water, or do we have to somehow calculate it?
We calculate 1.5 times 1000 and 0.5 times 800.
Okay. So we have to 1.5, right? Say again, please, Chris.
1.5 times 1000 plus 0.5 times 800.
Exactly, and that one was the water, and that one was the alcohol. Huh? Okay, so how much do we get for the mass of the water?
1500.
Okay, yep. And well, the other one is 400. Huh? Yeah, exactly. Huh? So in total,
1900.
okay, that's quite something. That's nearly 2 tons. Huh? So that's okay, quite a lot of mass involved actually. So and then we get what density?
Divided by 2.
No, exactly. So 950, huh? That would be kilograms per cubic meter. And as we've seen, everything was right because we had kilogram cubic meter, so no change of units. We had cubic meter here, we had cubic meter there. So that's like a final check to make sure we did not miss any power of something due to the cubing. Could have been suddenly a cubic decimeter, for example. Why not? But it's not. Okay, so it's 950. Henceforth, we go for question answer D. Huh? Okay, so that was not that complicated. Just seemed a bit complicated. Okay, so I mean, what you can see is that, in other words, because of the density relationship. So basically, it's like you have two relationships mass-wise, like 10 to 8, for example, and you have a relationship of the volume, which is 1.5 to 5 or 3 to 1, right? So out of that, you can actually realize as well what will be the ultimate density, of course. But that would be more math exercise than a physics exercise. Huh? All right. So, okay, now let's jump ahead and go into question 1. So we see multiple choice still, but the so-called hard questions. And let's see. So we have obviously something similar to what we just dealt with. goes a bit the other way around, so it becomes quite lengthy at some point. So we want to know the volume of water added.
So 1x so x will be the volume of water added. 1x plus
Okay.
1.3 times 40, and the entire thing divided by x plus 40 equals 1.1.
Okay. So was it 1.1 is equal to? Yep. Say again, please.
1x plus 1.3 times 40, and the whole thing divided by x plus 40.
Would you then not just say, okay, so you say 1x plus? So that x is the volume, right?
Yeah.
Is that correct? The volume added, huh?
Yeah.
The volume of water added, huh? Okay. And you say the volume of the water is plus which one?
The total mass of the glycerine.
Okay, so when you say 1, this is because you already multiply the density times the volume.
Yeah.
Okay, all right, okay, just to make sure. So it's not just 1x. Okay, and then you say the glycerine is 1.3, right?
Yeah. Thomas.
And you have added 40, right?
Yeah.
Okay. All right, okay. And divided by what?
The total volume, so it's x plus 40.
Okay. Let me just see the mass. Okay. All right. So now how to rearrange?
1.1 times x plus 40 equals the rest.
1.1 x
44.
plus, or you can say one, or I would say, should we already say 44?
Yeah.
Okay. Make it already a bit easier. And then we have 1. Okay, then we could just say x, huh? And 1.3 times 40 is how much?
52.
52, huh? Makes our life a bit easier, exactly. All right, okay. So that becomes rather simple now, right?
Yeah.
So therefore we can say 1.1 minus 1x equals 52 minus 44, huh? 8. Agree?
Yeah.
Okay. Then we have 8 divided by 0.1. Huh? And that is how much then, Chris?
80.
Yeah, very good. And in terms of dimension,
Huh?
what is the unit of measurement?
Centimeter cubed.
Yeah, genau, exactly. just to keep that in mind. Because like you see, of course, as everything's cubic centimeters, there's absolutely zero need to go to cubic meter. So as long as everything's on the same level and we put it into perspective, then of course, absolutely, yeah, that's very good. Actually, when I just had a brief look at the solution, they make it quite lengthy actually. So I like what you did. Sometimes, what I want to say with that is, instead of making it very, very explicit, it's explicit enough, so to speak, to put this one and say, okay, the mass of total over the volume of the total, right? So of course, let me do that again. Mass total over volume total. The only thing I would suggest is to say eventually here, well, what does that really mean? It becomes very obvious, but can just say, well, mass total is of course mass of this and mass of that, right? So water plus mass of glycerin. And of course, same thing for the volume. Total is nothing else but adding up the volumes. Volume of water, but volume of glycerin. It seems so obvious, but sometimes it's still worthwhile to do that. But then, of course, you come automatic from this. It's just, of course, crystal clear of what you're doing then. Huh? So this is just, you don't have to then start to write that down again and then put it together. You can just, like you did, can just jump ahead, so to speak, go into this one, but I would still list that one eventually. It's kind of very obvious. Of course, the total mass is the sum of the mass, but it may create, typically when it gets corrected, it would give some subpoints. If you miss it, of course, it gives no deduction as long as the result is correct. But if for whatever reason these numbers would be wrong, then at least that would save you a bit. Huh? Okay. Now, this one is a bit, okay. Block of wood, cylindrical, so more or less equal, like a cylinder. It's immersed in water with its axis vertical. So this is, usually we see the wood rather float on top and not necessarily like what they just say here. Floating here, we rather see it like that in tendency. But let's see.
The bottom pressure minus top pressure.
Okay. So.
And times
what do I?
Area.
Okay. Yup. So that would be this one exactly. Huh? Well, very good. Just straightforward, right? If of course pressure is equal to force over area, then of course it just goes pressure times area. That will become very automatic, like you just did it. Or eventually then the difference, of course. So Ainsworth, which one will it be?
C.
C, okay. Yep, good. So that seems not to be such a hard question. What do you think, Chris?
I think it's straightforward.
Yeah, right. So it's to find it in the hard section is a bit maybe the maybe why it's considered to be a hard question is to realize that the P must be greater than the PT. I think that is eventually the point, that to realize the further down you go, the higher the pressure, hence the upthrust is then the result of the difference in pressure. And that can only be then B minus T because B is greater than T. So something along these lines, I would say. That makes it maybe to be considered hard, but yeah, good that you looked at it a bit differently. And full fat milk. Okay, yeah, that's an interesting one. Because we have to go through a few steps. So the density of the fat. So we only want to know the density of the fat. So what is the core calculation we have to do? But it's nearly too simple. I mean, the starting equation. When you look at that. What do we have to calculate, Chris, ultimately?
Density of fat.
Yeah, exactly. And it's really absolutely straightforward, right? So density of the fat, which of course is nothing else but mass over volume, nothing new here. Sorry, that was the wrong way around. And how do we go now? How do we get that now?
The mass is
No, right? So when you look at the information you have, do we have the mass of the full fat milk?
we do have full fat milk at the volume of 1 times 10 to the power negative 3.
Mm-hmm. So we have the mass. Huh? So we have actually the volume and the mass. So for the fat milk, or the milk actually, so-called full fat milk, we have that one. Huh? So I call that the mass of the milk is green, right? We have it. Do we have the mass of the fat, or in other words, when we have the total full fat milk has a mass. So we have a density of the fat-free milk, right? How can we utilize that information?
I'm thinking we directly just put the 1.035 over 1 times 10 to the power negative 3, and then that minus the density of fat-free milk.
Okay, yeah, right. So yeah, you're right. I mean, what I wanted to drive at is because we want to know the mass of the fat. So I have the mass of the milk, also the full milk, so to speak. That's now a bit dangerous to say milk and milk. And when I deduct the mass of the I call that how do we call that? Basically, it's nearly like water, but it's not. But we can call that, well, the milk fat free. So call it the watery milk, huh? Just to say. So if I deduct the watery milk from the full fat milk, what do I get as a result, mass wise?
You get the
What is the difference?
mass of the fat
Yeah, exactly right. So I get that one. So that's not green, that's right. Blue. So I get that one, right? So the mass of the fat is the result of the difference between. So, and of course I have to make that red because I don't know. I called it the watery milk, huh? The fat-free. Or fat-free. Why not FF? Make life a bit easier. So called the fat-free milk, huh? Okay, so like you said, what? How do I get the mass of the fat-free milk? And you said it before, Tris, actually. Just say it again, please.
Mass.
Oh, you were close. You came a bit from a different. The mass of the fat-free milk is how much?
Because I don't know what volume.
Okay, let's go the other way around. So we leave that aside. Yeah, it's a good point. What about the density? So how can you utilize the density in order to get the volume? That's a bit the question here, right? You want to know the volume of the fat-free milk. So you could. There's one easy way to look at it. What does the 4% tell you? What does that tell you?
It's 1 times 10 to the power negative 3 times 4%. That is.
Okay. Yeah. Okay. So, or in other words, when you know 4% by volume is fat,
Yeah.
and we identified that the full milk or the difference, so it depends now on how we look at it. So this is equal to, you could say, for example, this is 4%, right? Not mass wise, but volume wise, for example. So, but in order to make it simple, say, well, volume and mass is actually, well, density times my volume, right? Do you agree?
Yeah.
Just straightforward, right? So as I have the density of the fat free milk. I just have to now to get the volume, which I don't know, huh? The volume of the fat-free milk. But what is the volume of the fat-free milk? By knowing that the fat is 4%. So you can say you have the volume of the milk minus volume of the fat. Huh? And you can go by percentage now. So the volume, this one is 100. This one is 4%. So what do you get for the volume of the fat-free milk?
Oh, 96%.
Exactly. So that is a bit the trick here, right?
Yeah.
To come up with that idea and say, hey, the volume is 4% of the fat. So to make, which is good because you come from this angle and say, okay, so you can apply the same logic a bit slightly adjusted and say, okay, everything's in a relationship here, right? The fat is nothing else but, of course, the difference between the two type of milk. That seems to be more water than anything else, but not only, but mostly. Doesn't matter. And on the other hand, the volume is given in percentage. So this is that double relationship here in order to come up with this one, huh? Because now I can, of course, say, okay, and 96% of 1,000 is how much? Because I want to have it in kilograms per cubic meter. So how can I deal with the 96% now, Chris?
96% times 1 times 10 to the power negative 3.
Yeah, exactly. No? So I can now say basically this is now 9.96 times 10 to the power of minus 3. Right?
Yeah.
Is that correct? Okay. Huh? So hence we get the volume. Out of that, we can make the volume. Huh? Or like you said, it's just this 96% times 1 to the power of minus 3. So it's 1 cubic meter. Now we have 0.96 cubic meter. Huh? So, and the fat is then just, well, obviously the difference, 0.04. And out of that, we can calculate, of course, the mass of the fat when we do that. So the mass of the fat-free, mass of the fat-free is how much? That was 1.040 times 10 to the power of 3 times 0.96 times 10 to the power of minus 3. Yeah? So hence, what is the fat-free?
0.9984.
0.9984. Okay, and in what unit of measurement?
Kg.
Kg, exactly. Okay, so that was an important step to know. So now that we have turned, basically I have to say it's green now. So this is this one. So I can get so hence I can get my mass of the fat. So mass of the fat henceforth is how much?
1.035 minus 0.0366.
Okay, all right. So something like 37 grams, huh? Okay. All right, now we have figured out that one out. And what is the last step now?
So times 1 times 10 to the power negative 3 with 4%. And we have the volume.
Okay. Okay, yep. So that was the missing one so far, huh? So we have 4, well, we just have the difference, right? So we have the volume of the fat is 0.4. No, well, it depends on how we write it. So what was the value you gave me, Chris?
So it's just 0.04 times 1 times 10 to the power negative 3.
Okay, yep. Exactly. So how can I make that into power, a bit more suitable for, well, usable powers, kind of?
4 times 10 to the power negative 5.
Yeah, exactly. It's a bit more helpful, right?
Yeah.
And of course, my volume here, what should I do with the volume? Well, that's disputable. You can leave it as well. Actually, it doesn't really help much here if I change that. So yeah, could do, right? We could, of course, do it. Let's see, let's count. So 1, 2, 3, 4. Yeah. So we could make it 366 times 10 to the power minus 4, but that doesn't really help. We need the calculator anyway. Okay, so henceforth we get the density is our 0.0366 divided by our 4 times 10 to the power of minus 5. Huh? And that gives us...
I got 840.
That should be higher. So 0. Let me just see, 0.0366.
Oh, wait, I typed it wrong.
Yeah. It must be, it's actually 36 divided by 4. That's 9. So it must be something with 9. When you look at it from that angle, like 36 divided by 4, right? Whatever the power is in the end. So it must be something with 9. And then, of course, some fraction. But when 6 divided by 4 is 1/5.
915.
So, yeah, exactly. Huh? And that would be what unit of measurement?
Kg per meters cubed.
Oh, exactly. Huh? All right. Okay. Very good. So we see fat as less than 1,000. That we had the density of the fat-free milk is higher, is 1,040 actually. So that's why fat swims on water, right? Same thing. A bit similar like with the oil, kind of.
Oh.
Okay. Chris, should I send you those 2 papers?
Yeah.
That you... I'll send you those 2, the medium and the hard one. All right, okay. I've taken a bit longer, but that's fine. So then not next Friday, no lesson, but then on Sunday, we will have the lesson Sunday in a week,
Okay.
All right, and a bit earlier. The time, I mean, I just tell you once more, let me just see. The time was, I think we said 11, but let me check. 11:15. I mean, sorry, that's my time. So that would be 6:15.
Oh, okay.
So Sunday, 6:15.
Yeah.
I mean, that has been between the center and your mom has been the timing agreed, but just that you keep it in mind as well. Okay, then have a good week and see you next week on Sunday.
Yeah.
All right. Thank you.
Bye. Okay. 2 hours and what? Why is this longer than what the hell?